Welcome everyone to our next edition of our TUM Distinguished Lecture Series on AI and Healthcare. And I'm super pleased that we can welcome Caroline Essert today. Caroline is at the University of Strasbourg, and she's also part of CNIS in France. She received her PhD of computer science and computer graphics in 2001 and her thèse d'habilitation in 2011 from Strasbourg at the iCube Institute, where she's been a professor since 2003. She's mainly working on computer graphics and geometry applied to preoperative surgical planning, most particularly for abdominal surgery and neurosurgery, computer-assisted surgery and navigation, virtual reality, and haptics for surgery. She has quite a few number of national and international grants on these topics and many exciting publications in this field. She even initiated a pilot software project for preoperative surgical planning. So this is really great, putting these things into translation. She's been involved in organizing several conferences in the fields of medical imaging, but also computer graphics for many years, including Eurographics 2014, CAST 2019. And of course, she was the general chair of MICA 2021, where we all were looking forward to visit her in Strasbourg, just such a short hop away from us. But unfortunately, of course, due to the pandemic, it was virtual, but it was a great success nonetheless. I was super pleased that she agreed to be nominated to become the next president of the MICA Society, and she was duly elected earlier this year. So we've got her for 3 fantastic years on the MICA board, where she's leading us. And for me, she's a fantastic role model, fantastic female scientist and leader who's always, very calm, but very assertive and always makes her voice heard. And I think this is why I was really pleased that she also accepted our invitation to speak today to us. And Caroline will be talking on modeling the surgical knowledge for computer-assisted preoperative planning. And I'm really excited to hear more about your work, Caroline.
Well, thank you very much, Julia, for this very, very kind introduction. And thank you all for inviting me to do this talk at your series of webinars. It's a good honor for me. So you already introduced me, so I will not present myself again, just say a few words about the University of Strasbourg and the iCube Institute. So you already know probably that it's located in the northeast of France, very close to Germany. Our institute was created in 2013. It's quite young, but actually it's resulted in the fusion of former laboratories. So it has a long history of research for decades already. And it has a little bit more of 600 members doing mostly research on computer science and engineering with a common interest in image in general. It can be satellite image, every kind of image actually. But there is a very large interest for biomedical imaging because we also have a cluster of research labs and companies working in the medical and biomedical field in the area of Strasbourg. So of course, our research focuses a lot in this kind of images. So the Institute has 4 departments. I'm with the computer science department and more particularly with the images group. Images is actually an acronym for images, learning, geometry, and statistics. This group is interested in mostly biomedical images, and my colleagues do segmentation, data reconstruction, registration, change detection, group comparison, brain connectivity, and of course surgical planning, which is what I'm going to talk about more particularly during this talk. But actually our team covers a wide spectrum of image processing in general, from macromolecules to clinical imaging, through biologic tissue, histopathology, and so on. So we cover a lot of disciplines. But I'm going to talk more particularly of surgical planning, which is what I really focus on in my research. So first, a word of what is surgical planning. So according to Wikipedia, surgical planning is the preoperative method of pre-visualizing a surgical intervention in order to predefine the surgical steps in the context of computer-assisted surgery. So it's how you prepare, how clinicians prepare the intervention using pre-visualization, so using mostly images and simulation to predefine, to choose the intervention strategy before the intervention. The transfer of the surgical planning to the patient is generally made using a medical navigation system. I will not talk much about this part, but of course it's of great interest, but I'm focusing more on the first part, which is helping the surgeon to make a decision, because it's a real decision-making process we're talking about here, and how we choose the strategy of intervention based on knowledge about the intervention and based on the images of the patient and the data of the patient. So computer-assisted planning is of course used in many fields of surgery, from, for example, maxillofacial surgery, or fractures reduction in orthopedics or cardiology. And I only put a few examples here, but I could cite many more disciplines of surgery. So it's a very wide area with very different problems and issues and very different ways to solve it. In this talk, I will mainly focus on percutaneous surgeries, which is a particular case of computer-assisted preoperative planning. So percutaneous surgery is when you perform an intervention without opening the patient. You just use a needle, for example, or you open a very, very, very small hole in the skull, for example, to insert an electrode. So the surgical tools are actually thin tools, straight tools like needles or electrodes. And the main issue with this kind of surgery is that you don't really see where you are actually doing the intervention. You do not see the pathology that you are removing or treating, or etc. So this is the main problem that you have. So what we want to do, we want to help the surgeon to prepare this kind of intervention. This can be done in abdominal surgery, for example, for the thermal ablation of tumors in the liver or in the kidneys, for example, or it can be done in neurosurgery, for example, for electrical stimulation of areas of the brain, such as deep brain stimulation, which is used to treat, for example, Parkinson's disease, or SEEG, which is used to diagnose and treat epilepsy. So percutaneous procedures are done using, can you see my mouse pointer? I can see it. Yeah,
you can see it, I think, yeah.
Yeah, yes. Okay. So thank you. So it's done using probes. For example, here you can see cryoprobes. They are used for cryoablation. So the principle of cryoablation is to destroy a tumor within, for example, the liver, without opening the patient. You put the needle and then you send an extreme cold, and this extreme cold will cover the whole tumor and will cause destruction of the cancerous cells. So here you can see cryoablation ice balls, which is the result of when you apply this extreme cold. So you can see that something like a small egg is covered by the ice ball and is destroyed. On the far right, you can see the result of another kind of thermal ablation, which is radiofrequency ablation. It's the contrary. You heat, you send an extreme heat to burn some tissue and destroy the tumor as well. But you can see that the shape of the ablation is more or less similar to the cryoablation. At the bottom, you can see examples of application of percutaneous procedures in neurosurgery. You can see deep brain stimulation, which is what is interesting in this image is that you can see Contrary to abdominal surgery, well, the needles are put more or less by hand like this. In neurosurgery, you usually have what we call a frame, a Lexel frame attached to the head, which allows to define very accurately the angle of insertion of the surgical tool. You can also use a robot. There is a robot called the ROSA robot, which allows to put very precisely the needle in the brain using shape recognition and registration. Here in the middle, there is an example of a stimulation electrode where you can see more or less that it's made of small metallic contacts that will send electrical stimulation. So I'll come back to that later. So why do we need computer assistance for this kind of interventions? Well, this is a very difficult task because, as I mentioned, you cannot see where you put the needle exactly because you do not open the patient. There is a dense network of sensitive structures, for example, dense vascular network, and you need to avoid the vessels, of course, if you don't want to have a hemorrhage. The shape of the pathology can be quite weird, can be hidden, can be located in various places of the body, and it requires usually high expertise and detailed knowledge of surgical principles, surgical rules of the intervention, general anatomy, patient-specific anatomy as well, and patient-specific data, and a lot of practice to be able to elaborate precisely the planning of the intervention, even if it's a simple straight tool. The other difficulty is that sometimes you don't have one straight tool, but several straight tools at the same time. For example, for SEEG, you can have up to 18 electrodes to put at the same time in the same side of the brain. So it can be quite tricky, not only because of the anatomy of the brain that you are putting the electrodes into, but also because of the interaction between the electrodes. You don't want to cross the electrodes and so on. So you have a lot of placement rules and strategies. So surgical planning is a time-consuming task that requires the attention of a lot of clinicians at the same time for quite a while. So you have two examples here. I took those two pictures. I attended staff meetings at UCL, at Pontchaillou, and at different hospitals, and you can have up to 5 or 10 people in the room trying to find the best strategy, and it can take up to half an hour, 1 hour, 1 hour and a half, and even sometimes 2 or 3 hours, depending on the difficulty of the case. So you can imagine the cost and the time it takes to those people to be for that long concentrated and focused on this task. So what we want to do is to automate the process and propose automatically strategies that are safe and efficient. So we want to build computer software to find automatically the best, the safest, and the most efficient trajectory for one specific patient and for one specific intervention. So the objective is to reduce the number of manual tasks that the surgeons have to perform, reduce time for the planning phase. We want to increase precision and safety as well, because most of the time it's so difficult that when the clinicians find a good spot, they are happy with that, and they maybe sometimes they can miss that another spot would have been better, more safer or stuff like that. So it's very difficult for them because they do not have always the good angle of view to make sure that the spot they chose is the best one. So using computer assistance would increase precision and safety. Another important point is that it would increase the number of potential patients eligible for a specific intervention, because sometimes they cannot find a trajectory that is safe enough, and they are sure that they will be able to perform this intervention without hurting the patient. So sometimes the computer can find an alternative and show that it would be feasible through this or this particular angle. And this way you can show that it's feasible for this patient. So you can include this patient and offer the surgery. So that's a very important point as well. So in this kind of computer assistance to surgery, what we want to do is to be as close as possible to the reality, to offer something that is feasible and doable. And we are sure that when we go to the OR, we find the same thing that was anticipated during the preoperative planning. The ideal tool would be adaptive and modular, because we want to adapt it to different types of surgery and try to include as many surgeries as possible and many patients as possible. And finally, what we want to have is an ergonomic design, an ergonomic visualization, interaction, and navigation, so that after the clinician has chosen a strategy helped with our tool, he or she would be able to reproduce the strategy that has been chosen into the OR. So that's the list of what we want to do. The planning is actually in the middle of a whole pipeline of things and research fields, I would say, between acquisition, image processing, 3D reconstruction. So that's where you get the data from. And on the other side of the pipeline, there is the outcome. So from the planning, we can do simulations to check things. We can do augmented reality or robotics to help navigate and guide the clinical gesture in the end. And you can even do telesurgery. So this illustration, you might already have seen it. It comes from ERCAT. So the to-do list when we want to make a computer assistance tool is for us to formalize first the knowledge, because we want to use the knowledge about the surgeries we want to help the surgeon with. We want to feed this knowledge base with data. We want to mix the knowledge and the data together to propose solutions that are as optimal as possible. And then when we provide one solution or perhaps a family of good solutions, help visualize the solutions and make the decision in the end. Because in the end, the clinician will always be the one who makes the final decision based on what we suggest and what we propose and what we display as informations. So a few examples here to show that actually surgical rules in our in the particular case of percutaneous surgery, surgical rules are usually placement rules, and they are mostly about geometry actually. So a few examples. The first example is that the length of the trajectory must be as short as possible, because if it's too long, there is a risk of deviation of the needle during the insertion. So we want the shortest possible trajectory. The second example of surgical rule is stay as far as possible to vital structures to avoid damages. For example, you want to be as far as possible from the vessels to avoid hemorrhage. If you hurt the vessel, you can cause a hemorrhage. So you want to be as far as possible to some vital structures. The third example is that the insertion angle mustn't be too tangent to the surface of the liver, for example, or of the surface of any organ, to avoid sliding on the surface. If you come too tangent, you can slide and not penetrate the organ. So those are three examples of surgical rules. So the work of the formalization is to translate this more or less into mathematical formula or geometric formula. So we can translate the shortest path rule into minimizing the distance between the target and the entry point. We can translate the second rule into maximize the distance between the surgical tool and the identified vital structures. We can translate the third one into the angle between the surgical tool and the organ surface must be above 30 degrees, for example, or 20 degrees, depending on what you have chosen. Then you can translate this into simple or not simple equations or formalized code. So that's great. You can have this. This is what a computer can understand. Okay, a mathematical formula or a piece of code that the computer can understand. The problem is that for any intervention, you have to list all those surgical rules. And of course, this is not a very easy task because, you know, a surgeon that is doing this for 20 years, they do this almost by instinct very often, and it's not easy to get the complete list of all the surgical rules. So it's a step-by-step process usually. But once you have the list of the rules, then you can write them down and include that into a geometric constraint solver. Question or problem: should we list and hard code all the possible rules for all the possible interventions? So we chose to avoid doing that. We chose to stay very generic, and I'm going to explain how we did that. But first, I'm going to notice that in those rules, there are what we call hard constraints or soft constraints. Hard constraints would correspond to feasibility constraints. For example, you cannot cross the ribs, you cannot cross the vessels, you cannot be too tangent to the liver. So this determines the feasibility of a trajectory. The soft constraints correspond to preferences. For example, I want to be as far as possible from the vessels, or I want to cover the target with the minimal possible effect shape, for example. So these are preferences. These are numerical constraints, whereas hard constraints are Boolean constraints. You satisfy them or you don't. So the approach would be, after this formalization, to do some geometric constraint solving that would treat, let's say, process the first type of constraints, the hard constraints, and some multiple objective optimization that would optimize the second type of constraints, the soft constraints that are numerical constraints to optimize. So in the end, we end up with this scheme that summarizes what we're doing. We gather patients' data, mostly images from MRI, CT, or other kind of images. We do 3D reconstruction and get some 3D scene meshes of the organs. We also gather information, knowledge about the interventions. We formalize the rules. We get a set of geometric rules, and we put together the patient data and the geometric rules and the formalized rules. We put them into the geometric constraint solver, and we get a solution space and possibly an optimal or several optimal solutions. And we then propose navigation into these solutions and the validation of a solution. So that's the overall scheme. So in the first part, we have to get the input, the patient-specific data. So this is done using image processing pipelines. So that's where I call my colleagues and say, okay, give me some pieces of code to do denoising, registration, atlas-based segmentation to get my 3D reconstruction. So we built a few image processing pipelines like PyDBS, for example, in 2010, that was proposed and presented at CARS. So the idea is to have a complete automatic pipeline to get the 3D models of the brain and all the anatomy of the brain based on T1 and T2 MRI, based on preoperative CT, and for validation purposes, we also used postoperative CT to get the final electrodes. And in the end, using a lot of image processing pieces of code put together, we built this pipeline so that we can get the full reconstructed skull and all the anatomy inside. So you can see a result, an example of a result here, a partial result, because not everything is shown, because otherwise we wouldn't see anything. So as an extra, what we did as well was to combine those models with another kind of information, which is also an input, an example of other kinds of data that is not coming from an image, but is coming from another kind of data. It's the clinical scores. So when you do electrical stimulation in the brain to treat Parkinson's disease, you can compute a specific score before and after the intervention that will help you know the degree of improvement of the symptoms of Parkinson's disease thanks to the intervention. So we correlated the clinical scores to the precise locations of the stimulation. That gave us an atlas of the parts that were stimulated and gave good results, and the parts that were stimulated and gave less good results. And this can also help guide the trajectory towards the best parts of the brain. So that's another example of data that we can use in our constraint solving. So apart from those kind of data, as I mentioned, we want to formalize the rules. So I already explained that we can translate natural language surgical rules into mathematical formula that can be expressed, for example, here as a tree, combining elementary operators like computing the maximum of two numbers or divide, subtractions, minimum distance between two shapes, etc. So it's elementary operators. We combine them with constants. Constants can be numbers or can be organs, meshes, 3D meshes. And we combine this with a variable. And in the end, we can move the variable and get the result and use an optimization function to get the best value of the variable to optimize this whole function. So when all our constraints are transformed into this kind of, let's say, trees or cost functions, we can solve in two steps. The first step is to define on the skin of the patient the feasible entry points. So that's when you solve the hard constraints, the Boolean constraints. Remember that the hard constraints is what you can do and what you cannot do. I cannot cross the ribs. So if I cannot cross the ribs, then those points that would lead from the skin to the target and would cross the ribs, it's not a feasible entry point. So solving those constraints allows to eliminate all the entry points that would not satisfy those constraints. So to do this, we used different methods such as GPU accelerated visibility functions to accelerate the computation of intersections. And we also worked on local subdivisions of the meshes to have more precise entry zones. Now, the second step is to solve the soft constraints, which are preferences. Problem is that the preferences can sometimes be contradictory. If I'm going back to one of my previous slides, let me go back to this one. Where is it? Sorry, just a second. Okay, this one. So if I come back to this one, remember I said that having the shortest path is better because it avoids needle deviation, but at the same time, I want to avoid being close to vital structures. So in this example, the top trajectory would be better for the shortest path constraint, but would be the right trajectory would be better for the avoidance of organs constraints. So sometimes it's completely contradictory because the shortest path goes close to organs and the longest path is very far from the organs. And it's just an example. You can have other examples of contradictions like this. So the problem is now, how do you combine all those constraints and find the best compromise? Because it's only that you can find a compromise between all those constraints that can be contradictory. So that's the point of the numerical optimization that we do next. So the first way to do this is to combine the cost functions into one super cost function, but unique super cost function. So you do this by using usually a weighted sum. So the idea is to put weights to each individual soft constraint, and you can adjust the weights. So for example, the surgeon I work with on abdominal surgery, they say that they don't mind if they go through the lung. Okay, they will hurt the patient, they will cause a pneumothorax, but in some cases, it can save the patient. And if they don't do it, they will not be able to save the patient. So in this case, they will put a different weight to the constraint of, organ avoidance. They take the risk of possibly hurting one organ if it can save the patient. Some other surgeon might say, oh no, I don't want to be very close to the organs. It's too risky. I want to stay safe. And I don't mind if my needle bends a little bit. At least I would be close to the target and I will burn a lot much to include the target, but I don't want to take too many risks. So depending on the surgeons, the adjustment of the weights can be completely different. So this is something we want to give to the clinician to do, adjustment of the weights. So when you do this, when you combine the soft functions into one single cost functions, what you get is individual color maps on the skin. That basically you color the feasible entry zone, and you put green where it's safe or where it's, let's say, satisfies this or this cost function, and you put red where it doesn't satisfy this or this cost function, right? And you have color maps individually for each cost function, and you have the combined color map that corresponds to the weighted sum of all of them. And with this, you can do a numerical optimization to find the best location or 2 or 3 best locations in this final color map. On a side study, we tried to see, using this method, what were the actual constraints that the surgeons were using more. The idea is to find how they set the weights implicitly. I mean, when you ask them, what do you consider as the most important constraints? They can tell you, I consider this one as more important, I will give it more weight, and this one is less important, I will give it less weight. But in the end, are you sure it's true, or is it their impression? So we wanted to check if they had the feeling of what they were actually doing. So the idea is that we took some retrospective cases, and we found it was deep brain stimulation. So in deep brain stimulation, you can take the post-operative image and segment the electrode, and with this electrode, you can find the weight that were actually used by the surgeon by browsing all the possible weights and see what weights gave this particular trajectory. And we found a very unexpected result, which was that in the end, the most weighted constraint was that they were using a trajectory that was the closest possible as the standard trajectory, which is 30 degrees anterior and 30 degrees lateral. And we think that this is a side effect of using the current commercial planning software, which propose as a basis of discussion this stand-up trajectory, and then the neurosurgeon adjusts the position of the needle around this trajectory and often doesn't search far away from this initial position that is suggested to them. So that's a very interesting information. Then we said it's weird because most of our colleagues in the world working on the same topic as I'm working on use the weighted sum, but in other disciplines close to us, like for example radiotherapy planning, or far from us, like finance or stuff like that, they usually don't do it because they know that the weighted sum has some flaws, some theoretical flaws, that they sometimes do not find all the possible solutions. And another way they are using in these other fields is they use a Pareto front, which is a real multiple objective optimization way of doing things. So the idea of the Pareto front is to find the different solutions that optimize at best multiple cost functions, but without orienting the choice in any way. So you evaluate separately the different cost functions without mixing them into one. You keep them separate, and you only use this dominance rule, and you eliminate solutions one after the other. So we implemented this way of doing this solution, and we wanted to know if the usual method, the weighted sum, was able in our field, in our application, to provide all the solutions of the Pareto front, or if the flow that is well known in other disciplines also happened to us. So we made this study that was published in MICA in 2016, where we compared both methods, and we asked some neurosurgeons to blindly rank the solutions given by one or the other method, and compare to his own manual planning. And the result was really interesting, because first conclusion was that the weighted sum was not able to provide all the solutions given by the Pareto front, which is a complete method. And the other interesting point is that, okay, we said it doesn't provide all the interesting points, but we don't care if the points that are provided are the best. Then we are not interested in the other points anyway. But in this study, we found that actually the missed points were the most chosen by the surgeons in the end. So it's very important that those missed points are not missed. So it's really better to use the Pareto front method, and all the teams, including ourselves, should stop using the weighted sum method. Okay, so I will not say more about this, the heart of the planning algorithms. I'm going to ask a question now, is that all I mentioned right before was about using preoperative images to provide a planning, but the problem is that these preoperative images are completely still, they don't move. So you don't take into account the deformability of the anatomy. You don't take into account the breathing, for example. You don't take into account the fact that the needle can bend, that the target can move, due to breathing or due to, for example, the simple fact that when you insert the needle, it puts a force inside the body and it deforms the body, and the organ in which the needle is inserted can be deformed and can completely move away from the planned trajectory. So we worked on that as well by including simulations into the optimization loop and trying to anticipate the possible deformation and trying to modify the initial entry point or the initial insertion direction so that we could reach the target with more accuracy in the end. So this is very important, as we noticed that using the static planning, we could have up to 16 millimeters of error if we don't take into account the possible deformability of the tissue due to pressure. Another kind of deformation that can happen in the anatomy is in the brain shift. So when you make even a slightly hole in the skull, you can have some brain shift. Like you can see here, some air entering inside the skull, which is the black part here. And it can completely deform the skull. And if you use the initial planning, then you can miss the target because it has moved by 1 or 2 centimeters. So in this study published in 2012, we tried, the problem is with the brain shift that you cannot predict the amount of brain shift. It completely depends on multiple factors. It depends on the patient, on the position of the patient, of the pressure in the brain, etc. It depends on so many factors that it's almost impossible to predict. So our approach was to say, okay, we cannot predict how much brain shift will happen. So then we will take into account all kinds of possible brain shift, from no brain shift to a lot of brain shift and an average brain shift. So all the possible brain shift, all the possible movements of the vessels or of the different parts of the anatomy are taken into account. And you can see here that after removing the parts of the feasibility area that were subject to potential vessel obstruction or stuff like that, then we only have a few remaining areas that are completely safe, whether there is a brain shift in the end or not. Another thing that we studied is try to anticipate the breathing. The problem is that when you plan something, usually the patient is at a particular state of the breathing. For example, the patient is asked to hold the breath while the image is acquired. And in the end, maybe when you insert the needle, the breathing cycle is not at the same stage. So it's a problem, and it's not a problem because sometimes in some cases, they stop the breathing for a short period of time, the time to insert the needle, or they use, shallow breathing, stuff like that, gating. But in some cases, it cannot be done for a very long period of time. So it's interesting to anticipate the breathing. So one possibility is to use what we proposed is to like a stop and start insertion technique, where you observe for a while the movement of the breathing and the different anatomical structures, and you can detect if at some point a specific structure will come into the trajectory. If it's the case, then you can deflect a little bit the needle, or if it's not the case, if it at some point it moves out, then you simply wait that it's out, and you can go on with your trajectory. What we also studied is the effect. So because of course, when you want to optimize the position of the needles or the electrodes, you want to optimize the effect around the target. So we considered in the context of thermal ablation, we computed the propagation of heat using the Pence bioheat equation and simulating the propagation of heat and see what was covered around what tissue was covered around the needle. The difficulty here is the computation times, of course, because if you want to include this in the optimization loop, you need to have a very fast simulation. And the second difficulty is the presence of vessels or the presence of liquid that is here to protect some other organs that is inserted by surgeons. And all these vessels and the liquid are at 20 or 37 degrees and will impair the capacity of the cold to propagate. So that's what we did here by taking into account the vessels in the simulation. And as you can see here, we were able to compute an ice ball that is deformed due to the shape of the vessels. So this has been done by computing this on GPU and was also presented at MICAI. Another challenge for the surgeons is when they want to do the insertion of the needle inside the gantry of a CT scanner, for example. And when they want to do it with a robot, it's even worse because the arm of the robot has to go above the patient and below the gantry. So in this short study, we also tried to define the accessibility areas for a robot to reduce the possible insertion points. Now, everything that I explained was mostly for one insertion, one needle or one electrode. But what about multiple tools? I mentioned earlier in the talk that for SEEG, for example, for epilepsy, you can have up to 18 electrodes at the same time in the skull. So that's one of the difficulty. For cryoablation, you can have up to 4, 5, sometimes 6 needles at the same time interacting together. So we already talked about the simulation of interacting needles. I'll talk a little bit about epilepsy electrodes. So our goal, so it's an ongoing work, it's not finished. I will show some preliminary results. Our goal is to try to use machine learning. So as you noticed, probably it's been like 40 minutes that I'm talking, and I have not mentioned deep learning or machine learning so far. So that's the moment where I mention it. We want to use deep learning to help find the best positions for these electrodes that are very numerous. So to do that, we need to have training data, and to have training data, we need to have data that are annotated, and to have annotated data, we need to be able to segment the metallic contacts that we can see as white dots here in the intraoperative image. The problem with automatic detection of these contacts is that there is a lot of artifacts on the image due to the presence of metal. So we proposed I'm going to rush a little bit because I see that I'm a bit behind the schedule, but if you're interested, you can still contact me. So the first method was not using deep learning, using traditional image processing to do that. The conclusion was more or less good, but not completely satisfactory. So we moved to using 2D unit and 3D unit to do that. And we realized that both methods, both models had flaws or drawbacks. The 2D unit was very sensitive to the artifacts, while the 3D unit was very sensitive to the location of the contacts. I mean, the contacts that were close to the skull were often missed. So we tried to propose a hybrid 3D and 2D 3D unit that takes the best of both worlds. And we were able, thanks to this hybrid unit, to have a better detection of external contacts close to the skull and to be less sensitive to artifacts. So that's a nice result that is currently submitted. And we also did something that I liked quite a lot, is to propose to build synthetic training data to do data augmentation. So the idea is to move to the sinogram to create those data. We use an MTCT. We put a random electrode somewhere, or several random electrodes somewhere, in constraint places to be realistic still. And then we simulate the artifacts that are present in the real images. So to do that, we take the empty image, we take images of metal only, we go to the projection space and build the sinograms of all that. We do some specific treatments, and then we combine both, and in the end we go back to the image space and get this nice image with the metallic artifacts. So with this, we proved that using this kind of specific synthetic training data, we were able to increase the accuracy in the detection of images in new real cases. Now, when we have provided some assistance to the surgeon to choose the best strategy of intervention, how do we get the plan to the operating room? So don't worry, I'm not going to open a new chapter of my talk here. It's almost the end. It's my last slide, because it's what we want to do from here. We want to go towards navigation. Now we have the planning. How do we couple this with real-time navigation and real-time replanning? That's what interests me the most, real-time replanning, in case in real time we realize that what we had planned is not possible anymore for any reason, like movement or whatsoever. So that's maybe for my next talk. Thanks for your attention, and I'm open to questions.